Okay, so I'll start by providing a brief summary of what I did in yesterday's lecture, and I hope I didn't lose you during the course of the lecture, and I was able to get across some of the important concepts associated with evolution in finite populations. I'll start by showing one of the simulations that I wanted to show to emphasize how just random process of update of the population can lead to an equilibrium state which consists of just one type only. Okay, so here's a NetLogo simulation. NetLogo, for those of you who don't know, is a very useful tool for carrying out agent-based simulations. They have a lot of inbuilt programs already, and this is one such inbuilt program that is there, which is called genetic drift. But it's essentially the kind of simulation that I was talking about in yesterday's class, where you start off with a population of, say, two types of individuals, here represented by red and gray squares, and ask how is the population going to evolve if I just pick an individual at random for reproduction and pick another individual at random for death. Right? So I am updating the population using a Moran process and asking how the population is going to evolve. So what this model does is to put it on a 2D lattice, and essentially using the same algorithm, you pick every lattice you see has a definite color, and to update the population, you choose another color from the entire space to update the particular lattice site you are at. And you choose another lattice site at random from the entire space, and if it happens to be red, then this red square remains unchanged. If it happened to be gray, then it is replaced by gray. So this is how evolution proceeds, and if I start the ball rolling, you will see that these colors obviously change, the pattern changes, and the numbers also change, but you can see fluctuations, and once in a while one color will gain an advantage over the other, right? And that advantage can become larger and larger over time, but it can also revert back. As you can see from here, it goes up and then goes down again, and so on. And you can see that ultimately, if you run the simulation many times, you will always end up in a state which is either completely red or completely gray. Okay, and yesterday we saw that we could actually calculate the probability with which one of the colors would take over the entire population given an initial configuration where that particular color had a certain was represented a certain number of times. So if I rerun this simulation again, you may end up in a state where a different color, gray, becomes fixed. So in order to calculate the fixation probability of a particular color or particular type, you have to repeat the simulation again and again and ask the question, how many out of those trials, how many times out of those trials is the red type getting fixed, and how many times out of those trials is the gray type getting fixed, right? And there's no selection here, so it's a completely random process. Just by pure chance, one color or one type is gaining an advantage over the other, so it's if you start off with equal fractions of both types, then it's equally likely that one of them is going to take over, right? Okay, so let's go back to the So here are the key take-home results of yesterday's lecture. We saw in the case of neutral evolution between two different types, we could calculate what's called the fixation probability. There's a bit of subtlety that I forgot to mention in yesterday's lecture. In the literature, you will also find the term invasion probability being used quite frequently. And invasion probability and fixation probability are similar concepts. So invasion probability corresponds to a scenario where you start from a population where there is a wild type and there's just a single mutant. Okay. So if the population size is n, there's one mutant in the population and n minus 1 wild types, and you ask the question, what is the likelihood that this single mutant can take over the entire population? Okay. So in that sense, the mutant is invading the wild type population and taking it over. Okay. Whereas fixation probability is a more general idea. So you can start off with a configuration in which there's a different fraction of both wild types and mutants, and you can ask, given a certain number of mutants in the initial population, what is the probability that it can take over the population? Okay. So we calculated the fixation probability, or rather the invasion probability, to be more accurate for a neutral evolution case, and we found that this is proportional to 1 by n, so inversely proportional to the population size. Okay. So what about competition between two different types of organisms or species which have different fitness? We saw that in finite population, the higher fitness individual is not guaranteed to take over the entire population, but it is more likely to do so than is dictated by chance. And we were able to calculate general expressions for the, I didn't do the calculation explicitly, but I showed the steps to calculate the general expression for the fixation probability starting from a state where there is just one type. The number of individuals are I to begin with, and out of n, and then you ask what is the fixation probability that it takes over. Okay. So these were the general expressions which I am going to use quite frequently in today's lectures. The simplification that was carried out, that was possible in the neutral evolution case, is because this factor, which is the ratio of the transition probabilities for the Moran process, happens to be 1 for the case of neutral evolution, and that allows you to carry out this complicated sum and product operations quite easily, and that leads to this kind of result. Okay, so just to recap and give a brief summary of all that was covered in Shagor's talk, I want to go from a situation where I was talking about evolution with constant fitness to evolution with frequency dependent fitness. So when I talk of evolutionary game theory, it is nothing but evolution with frequency dependent fitness. Okay. So individuals have fixed strategies, and in a biological context, the strategy can be thought of as a phenotype, just like the patterns on a leopard's skin or the ability of a deer to run fast. And the payoff can be associated with fitness, the payoff that results from two interactions between two strategies. And fitness is a measure of reproductive success. So the key concept in evolutionary game theory is that the fitness is not a constant, but it depends on the number or the frequency of other types that are present in the population. Okay. So fitness is a measure of reproductive success, but fitness is frequency dependent, and that's the key, and that seems obvious because the fitness of a deer in this kind of environment is going to be very different from the fitness in this environment when it is being chased by a leopard. So this concept of fitness as a frequency dependent quantity is is symptomatic of evolutionary game theory. So okay, so a brief recap of the replicator equation which you may have already encountered. So I'll keep going back and forth between deterministic models and stochastic finite population models, so it's useful to understand what the replicator equation has to tell us. Here the fitness is no longer constant but depends on the frequencies of the two types A and B. So the fitness of A depends on the frequency of both A and B, and the payoff that you get when A is interacting with another A, and B is the payoff that you get when A is interacting with B. And similarly, you can write down the fitness for B, which also depends on the frequency of both A and B in the population. So C is the payoff that you get, that B gets when B interacts with A, and D is the payoff that B gets when it interacts with B. And so this is the usual payoff matrix, a slight change in notation compared to what you saw before. Instead of RSTP, I'm using ABCD. I should have better coordinated the talk, did not cooperate enough with Shagor, I guess. Okay, so when you plug in this expression for fitness into the replicator equation, you get an equation in this form. It's a simple equation for just two types, and you can solve it by hand. And when you solve it by hand, you find that depending on the relationship between the payoff elements, four possibilities arise, right? One is the case, and this is was just mentioned by Shagor in his talk. So if you have a situation where the payoff to A when it interacts with A is larger than the payoff that B gets when it interacts with A, it means if both strategies are playing A, both players are playing A, and one of them switches to B unilaterally, that person ends up with a lower payoff. And so when that happens, this becomes a Nash, and if B is also smaller, is also larger than D, then the only strategy that is Nash is A here. And so by looking at the payoff matrix, you can figure out which strategy is a Nash, which of the pure strategies is a Nash, are both pure strategies Nash, or whether none of them is a Nash, right? So it all depends on the relationship between the different elements of the payoff matrix. The prisoner's dilemma game corresponds to the situation where only D here, I should have written CD instead of AB, but think of this as D, this is C. So only the defector strategy is a Nash, and so in these two cases, there's only one stable equilibrium state. In the case of the harmony game, the equilibrium state corresponds to one where cooperators take over the population, cooperators dominate because that is the only pure strategy which is a Nash. The prisoner's dilemma game is one where defectors dominate, that's the only pure strategy which is a Nash. And but there are these other types of games like the stag hunt game or the coordination game, where you have it is better for you to coordinate your action with that of your opponent. So if your action matches with that of your opponent, you get a higher payoff instead of the situation where your action is just the opposite of that of your opponent. And in this situation, there exists a mixed state solution whose frequency is given by this quantity, and this is an important quantity which I'll come back to again and again. So when you solve this equation, you put this term equal to 0, that gives you a mixed state equilibrium solution, but the mixed state equilibrium solution is unstable. So in this example, in the stag hunt example, what is the Nash equilibrium here, right? Both strategies are a Nash, right? If both of them are playing cooperate and one deviates, you end up with a lower payoff. If both of them are playing defect, one deviates, you end up with a lower payoff. And so if but which of the Nash equilibrium states will you end up in? And that depends on where you start from. So since the mixed state is an unstable equilibrium state, if your initial frequency is larger than the mixed state equilibrium frequency, you are going to end up in a state where D is the Nash, where the population consists of only D. But if it's smaller than your mixed state equilibrium frequency, you are going to end up with a state in this state here, right? And in the other type of game where none of the two pure strategies are a Nash equilibrium, but there exists a mixed strategy which is a Nash equilibrium, then you can show that the mixed state equilibrium is a stable equilibrium, and so depending on your initial configuration of the two strategies, you are always going to end up in a mixed state. Okay. So this is the summary. So what we are interested in is looking at evolutionary game theory with the aim of understanding the problem of cooperation. Yeah.
I should have asked this before, but this dynamic should preserve that normalization that X essentially equals.
Yes, absolutely. Yes. Because I ensured that I was able to decouple the two equations.
Let's say I have many A, B, C, D, E, F.
Yeah, then you cannot.
Is there some feature that you put into the intent that the evolution doesn't, that takes care of this one?
No, you cannot decouple the equation, all the equations. Then you have to deal with the. If you have three strategies, you can reduce one by using the condition that xa plus xp plus x equal to 1. But then you end up with 2. And so this was a simple case. That's why I chose the one with 2 strategies. And 2 strategies are what you deal with in most game theoretic contexts, right? So any questions so far? So this was just a recap of what was done in Shagor's lecture. And so what we want to understand using the framework of evolutionary game theory is the problem of cooperation. So why is it that altruistic behavior is sustained in the population despite the fact that altruistic behavior comes at a cost, whereas selfish behavior is cost free? And so this is a key problem in evolutionary biology right from the days of Darwin, who also realized it, especially in the context of social insects like bees and wasps. And it remains a compelling problem to this day. So we want to understand how cooperation can be sustained in a population. But in order to understand that, we have to ask some difficult questions, right? So we need to understand how, so cooperation is a behavioral trait, right? And so we need to understand how individual behavior changes over time, and how does it depend on the size and the structure of the underlying social network, say, like all of us are embedded in when you're talking about people. How does it depend on who your neighbors are and how they behave with you and with other people? How does it depend on the economic and social milieu in which you are embedded? And how does it depend on your own aspiration levels, right? So these are all complex factors. So the key question is, how do we incorporate all these factors into learning strategies that we can apply when faced with a social conflict situation, and which allows which would eventually allow cooperation to thrive, to be at least sustained in the population. So we want to understand how do individuals incorporate these factors into their learning strategies. We want to understand how these factors shape collective evolution. And we also want to understand whether we can socially engineer situations where cooperation thrives. So what do I mean by social engineering? So you can have a situation where if you are selfish, you are punished, right? It may be written in some legal framework. You can have situations where your income or wealth is revealed to the entire community, so that everybody knows how much you are making, how much taxes you are paying. In fact, that is done in some Scandinavian countries, Norway for sure, maybe a few more, and so on. So can we socially engineer situations which allow for cooperation to be sustained? So the fact that it's an important problem is probably not lost on you, but some years ago the journal Science celebrated 125 years, and they came up with this list of 125 important problems in science, and how did cooperation evolve happened to be one of them. So it's really goes to show how important it is. So what are the mechanisms of sustaining cooperation? Shagor touched on this very briefly towards the end of his talk. So this is a slide that's taken from a very nice review by Rand and Novak, which says the different rules for spread of cooperation. So one mechanism is direct reciprocity, which Shagor talks about. So if you use strategies which cooperate when the other person cooperate, okay, then you are directly reciprocating the action of your opponent, right? So tit for tat is an example of a strategy which is a reciprocal strategy. I cooperate if the other person is nice to me, I defect if he is mean, right? So these form a class of strategies, and a lot of work has been done in order to understand what sort of reciprocal strategies can do well in terms of sustaining cooperation. Another mechanism is called indirect reciprocity. So this is based on the fact that no good deed is carried out in vain. So other people observe what you have done and ascribe a reputation to you. And based on your reputation, you can be the recipient of altruistic acts or selfish acts. So if you have been nice to people in the past, other people are going to be more likely to be cooperative with you rather than vice versa. So this is a reputation-based mechanism of spread of cooperation. It's not something that I'll have time to talk about. Yeah. Sorry, which one?
The economic status of the person, that also form the reputation of the
What do you mean by economic status?
So what we're saying is, based on the actions that the person has taken, a social reputation is assigned to a person, whether they're nice or they're not. And so can the economic status of the person also contribute to the reputation? Or
so if by economic status you just mean wealth, so it can. But more importantly, if a wealthy person is found to be a philanthropist as well, donates to a lot of causes, so that gives a signal to others that he cares about social good and all. So that kind of that is a kind of reputation I am talking about. So if you are performing an altruistic act when you are interacting with others, that helps you build a good reputation. So there's a lot of work which talks about what do you classify as a good reputation and what do you classify as a bad reputation. Is defecting with a selfish person good or bad? And so there are these social norms which one can talk about, which classify how your reputation has to be judged. And so indirect reciprocity mechanisms talk about these different social norms. So they are, I mean, one can talk of indirect reciprocity only in the context of specific social norms, which allow you to classify which action is good and which action is bad. Okay. Okay. So there's another mechanism called spatial selection, or the effect of structured populations, which says that if you have a population which is structured and not well mixed, in the sense that a member of the population can only interact with some with her connected neighbors, then that brings an additional level of complexity into the problem. And one can show, as I will in tomorrow's lecture, how such spatial structures or network structures can aid in the spread of cooperation compared to well-mixed populations. There's a mechanism called group selection and kin selection, which I'll not go into, so let me not spend time on that. Okay. Okay, so just a very quick review of an ESS. So you probably know by now that ESS is the condition of an evolution for a strategy to be an ESS was obtained by asking whether a mutant can invade a population consisting primarily of A types, where B is a mutant. And in the context of infinitely large populations, so what you do is start off with a very small frequency of mutants given by epsilon, and ask what is the fitness of the mutant in the population and what is the fitness of the wild type in the population. So the fitness of the population in the mutant is frequency dependent, so it depends on the wild type frequency as well as the mutant frequency, and it's given by this. And similarly, the frequency or the fitness of the wild type can be calculated in this way. And we know we then impose the condition that B will not be able to invade A if the fitness of the wild type is larger than the fitness of the mutant. Okay, and so that leads to these conditions on the elements of the payoff matrix. So by looking at the payoff matrix, you can tell which of the two strategies, pure strategies, is an ESS or not. But now let me come to the crux of the problem. I talked yesterday about the fact that in finite populations, even deleterious mutants can get fixed, right? And so how do we extend the concept of ESS to finite populations? And how does population size affect the survival of cooperative strategies? So this brings us to this topic of games in finite populations. So what we have is a game which is given by this kind of payoff matrix. It's a most general kind of payoff matrix. I have not specified the particular values of the elements of the payoff matrix here, but we know that this condition, I mean, you can think of this as being a prisoner's dilemma game where C is a cooperator and D is a defector, right? And so in order to understand how a population size or finiteness of the population affects the ESS condition, we need to calculate fixation probabilities. And we can calculate fixation probabilities from using the formalism that was developed earlier. So suppose you have a population of C and D players, and you ask, so you have to calculate first the expected payoff, the fitness of a C player in the population, and a fitness of a D player in the population. Now, assume that the population is well mixed, so anybody can interact with anybody else. So the probability that a C interacts with another C will depend on the frequency of the C's in the population. So there are I C's to begin with. So the probability that C interacts with another C is given by I minus 1 divided by n minus 1. You have pulled out one C, which is the focal individual who is going to interact with another C. So there are n minus 1 individuals left in the population and I minus 1 individuals of type C. So the probability that the C that you have pulled out as a focal individual interacts with another C is given by this factor, right? So in the same way, you can write down the probability that C interacts with D, D interacts with C, and D interacts with D. Now, once I have obtained the probability that each of the type interacts with another, I can calculate the payoff. So how do I do that? So the total expected payoff is given by the probability, the expected payoff to C when it interacts with C, plus the expected payoff to C when it interacts with D, right? So this is the probability with which a C interacts with another C, and when they interact, the focal C player gets a payoff equal to small a. This is the probability with which a C interacts with a D, and when they do so, the focal C player gets a payoff equal to small b, and so the total expected payoff for the focal C player is given by this quantity, okay? And similarly, you can calculate the same thing for the focal D player, and this is the expression that appears. So now we can, so this is a payoff. So this results only from interactions with other players in the population. But there can be an intrinsic fitness associated with an individual, which has not been taken into account. So we can define fitness as in this form, where we introduce a parameter W, which is called the intensity of selection. It will become clear why it is so called later on, where the fitness is, so this essentially tells you what is the likelihood that the fitness to an individual is determined by its interactions with other individuals, and to what extent is its fitness dependent on its own intrinsic fitness, okay? And so in this format, I have assumed that there's, if you look at just the intrinsic fitness, there's no difference in intrinsic fitness between the two players. So this quantity is 1. So W is the strength of selection. So when W equal to 0, it means that there's no difference in fitness between the two at all. So the total fitness of the individual does not depend at all on interactions with other individuals. When W equal to 1, it means the fitness is determined completely by interactions, and the intrinsic fitness doesn't come into the picture at all, okay?
If I want to recover the mean fit picture, that I can do by replacing the probabilities with the fractions, and there is no intrinsic fitness. That recovers the.
Yeah, but there for the intrinsic fitness, you have to replace 1 by Fa and Fb.
W is 1, then I recover the original replicator kind of thing.
Yes, 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 exactly. Yeah. Okay. Yeah.
This confuses. How is intrinsic fitness different from C interacting with C?
So intrinsic fitness is not a fitness, not a component of fitness that arises as a result of interactions. You know, I have an intrinsic fitness because of whatever my quality of life, my current health situation, and so on. But there's also a component which can contribute to my fitness, say when I'm interacting with someone who cheats me, and and I lose a lot of money. So in that sense, the interactions also contribute to your fitness. So in the example of the deer and the thing, so when the deer is interacting with a group of other deers, then its fitness is different from when it's in this situation, right? But it also has an intrinsic fitness of its own, apart from the interaction part. Yeah.
Can you go back to that slide?
Yeah.
What is the 1 minus W term?
So 1 minus W, so this is just how it's parameterized, right? So it says that when W equal to 0, Fi and Gi are the same. So W is the extent to which the fitness is determined by payoffs that appear from interactions. So if the fitness is not determined by payoffs that appear from interactions, then these two quantities have the same fitness, and both are 1, right? But if W equal to 1, it means that the fitness is completely determined by the payoffs that result from interactions with other individuals in the population. Yeah.
So W depends on the fluctuation in the payoff for CNT.
W is just a parameter. It's just a parameter. I can assign values to W, and the reason it's introduced is because analytical calculations, especially in the context of Moran process, is possible only in the weak selection limit, where W is much smaller than 1. And so the weak selection limit essentially says that the contribution of interactions to fitness is rather weak. And but if W is large, 1 for instance, then it means that so that violates weak selection criteria, right? So it means that the total contribution to fitness comes from the interactions with other members of the population. So for finite populations, as I said, we need to so if you ask the question, when can a population of D players avoid being invaded by a single C mutant? Just by looking at the payoff matrix, what can you say? You can say that D players, if D is an ESS, which is the infinite population result that we just showed, if D is greater than B, or if D happens to be equal to B, then C must be greater than A, right? So just by looking at the payoff matrix, you can say in the infinite population scenario, which of the strategies is an ESS. But for finite populations, the results change a bit. This is just a glimpse of the results which I am going to obtain. So here I have to, so how did I get the ESS condition to begin with? Or rather, how did Maynard Smith arrive at the ESS condition? So he said that if you start with a population with a very small fraction of mutants, and then calculate the fitness of the mutant using this frequency dependent fitness relationships, and calculate the frequency of the wild type, the condition for a strategy to be an ESS depends on whether the wild type fitness is larger than the fitness of a very small fraction of mutants that has been introduced into the population. So if I want to translate this condition to the finite population scenario, I can ask so D is the wild type here, C is trying to invade D. So I can ask, if I introduce one C into the population of n Ds, so there's one C and n minus 1 D types, then the fitness of one C in that population has to be fitness of one C in the population has to be smaller than the fitness of n minus 1 Ds. So this indexing you have to be a bit careful with this indexing. The index I here corresponds to the number of C's in the population. Okay. So when I say F1, I'm referring to a situation where the number of C's in the population is 1. And the number of D's in the population is n minus 1. So G1 means that the population consists of n minus 1 D's, and I want to calculate the fitness of a population of a D when there are n minus 1 D's and 1 C. So this condition for ESS, if I want to translate it to finite populations, I am going to ask if the fitness of one C has to be less than the fitness of n minus 1 D's, right? And this we will show you. I just wrote down the result here. This leads to this condition. Now let's take the large n limit of this result. What does the large n limit give you? It gives you that B is less than D, right? But if you compare it with the infinite population result, it doesn't match. So the infinite population ESS condition is neither necessary nor sufficient for this. Look at the case for n equal to 2, and that highlights this example, this fact the best. So for n equal to 2, I have B less than C, whereas for the infinite population result, the ESS condition is D has to be less than B, right? And so these two conditions are completely different. So for small population sizes, the ESS condition is completely different when you just impose the condition that a fitness of a single mutant has to be smaller than the fitness of n minus 1 wild types. And similarly for this as well. Okay. So where is the catch? So what do we have to do in order to obtain the appropriate condition for ESS in finite populations? So we need to consider fixation probabilities in finite populations in order to determine. So it's not enough to say that the fitness of an individual of a mutant is less than the fitness of the remaining wild types. You also have to make sure that the mutant has a lower invasion probability than what you would expect by chance. So that's why what would you expect by chance? That is your null hypothesis, right? So for what you would expect by chance is a neutral evolution result. Yeah.
So you applied probabilistic arguments to cognitive here.
Yeah.
So doesn't that already require a large enough? So can you actually put anything to prove it? Here that
I can always calculate the probabilities regardless of what the values of n is.
For us, probabilities only work in a large population. So n would need to be sufficiently
right.
So
right.
you can't actually use it for n is equal to 2.
Yeah, you can. I agree, and I'll show you a situation where for n equal to 2, it gives kind of weird results, but if you do it for a large but finite n, then you can talk of probabilities as well, right? Even in that case, you have to decide what the condition for ESS is, right? Because if we have seen, the key point that I cannot emphasize more is that in a finite population, any of the two strategies can take over the population, right? So the question is, how do you then decide on an ESS condition? ESS condition says that, I should not allow a mutant to invade. But in finite population, even if a mutant which appears has a lower fitness, it has a probability of taking over the population just by fluctuations, as a result of fluctuation. So the condition for ESS needs to be revisited. And so what is essential is that we calculate, we incorporate fixation probabilities and say and add additional conditions on the fixation probability to obtain the new condition for ESS, which is population size dependent. So this condition is valid. If this is valid, it means that selection favors C in replacing D, right? So even if the fitness of a single C mutant is less than the fitness of the remaining D wild types, C can still invade if its fixation probability is larger than what you would expect by chance. Okay, so now this is a dense slide with a bit of calculation, so I'll just go through this quickly. So Moran process, so I can use the framework that was developed for Moran process and apply it to the case of two strategies which are interacting with one another using this prisoner's dilemma kind of game. And I can calculate the transition probabilities. So since I'm using Moran process, the population is changing only one individual at a time. So the number of C's can increase by 1 or decrease by 1 or remain unchanged, and these are the probabilities with which it can increase by 1. This is the probability with which it can decrease by 1, and this is where the frequency dependence comes into this factor, right? So I is the number of C's, so this is the average, the probability with which you pick a C, which depends on the frequency of C's in the population or the number of C's in the population. And if you have the transition probabilities, you can calculate, you can just plug it in back into this, these expressions, which were the most general expressions that we obtained, and calculate the fixation probabilities. So all you need to do is to calculate this complicated sum product thing. Now this calculation is not very straightforward. That is why we have to go to the weak selection limit. And in the weak selection limit, it is possible to calculate these quantities, and when you calculate these quantities, you end up with this condition. Okay. So you can see that this is a condition which puts a constraint on either n if A, B, C and D are fixed, or A, B, C and D if n is fixed, right? And in the limit of large population sizes, it reduces to this condition, which has very interesting consequences, which I am going to talk about. So how am I doing on time? Is it over? Okay. Okay, so I'll just finish this slide and just these two slides and then stop. So for fixed A, B, C, D, this reduces to a condition on the population size. So fixation probability of C is larger than what you would expect by chance. In that sense, C mutant will be able to take over a population of D wild types only if the population size is larger than a certain critical threshold, right? Otherwise, it won't be able to invade, right? Or if the population size is fixed, then this condition has to be satisfied. Now, what does this condition mean? So we can draw a nice correspondence with our infinite population result, right? So what this condition means is it translates to this condition, and if you recall the mixed state equilibrium frequency, then you can see that if you use this condition into the mixed state equilibrium frequency, it imposes a constraint on the mixed state equilibrium frequency. So if you look at your infinite population model, calculate the mixed state equilibrium frequency, and that happens to be less than 1/3, you can say that the C mutant is more likely to get fixed in the corresponding finite population model. So this is a plot which shows the different regimes. So this is your phase diagram, or this fixed point diagram. So this is x equal to 1. This is the mixed state equilibrium frequency. This is a value at which the mixed state equilibrium frequency is 1/3. So in this regime, the fixation probability of C is larger than 1/n. So if in the corresponding infinite population model the mixed state equilibrium frequency happened to lie in this regime, then in the finite population case, C can invade a population of D wild types. But for this, if it lies anywhere else in this regime, it cannot. And similarly true for Ds. If D can invade, if it's in this regime, otherwise it cannot. Okay. So there's a nice correspondence which appears between the infinite population result and the finite population result. You can look at the mixed state equilibrium frequency in the infinite population replicator dynamics and then predict whether in the finite population scenario a mutant can get fixed in the population or not. Okay, any questions?